We're now going to learn about some more complicated ways to describe sound. So the first thing we'll do is learn how to describe sound waves. Describe sound waves. And then compare how sound moves through different materials. Moves through materials. When we're describing sound waves, one term that we need to be able to use is frequency. Frequency. Which means how quickly are the vibrations happening in the object that's making the sound. How quickly are the vibrations happening? We can describe frequency as either high or low, and the frequency of the sound determines the pitch that we hear of the sound. And pitch is just another name for, is the sound high or low? So frequency causes the pitch of the sound that we hear. The second term to learn is amplitude. And amplitude means how strongly is the object vibrating. How strong are the vibrations? If an object that's making sound is vibrating strongly, that means the sound will be loud. And on the other hand, if something is not vibrating strongly, that sound will be quiet. So loudness is caused by amplitude. Let's look at a sound wave again to practice using these words. So here are some particles with a sound wave moving through them. Remember, sound waves moving through particles have areas of high pressure, which are called compressions, and areas of lower pressure, which are rarefactions, where the particles are more spread out. And the sound waves move away from the direction of the object that makes the sound. Let's say it's a person yelling out in this one. So the frequency of the waves in this example are how often the compressions and rarefactions are made. And in this case, I'd say this is about an average frequency. Let's compare this to another example though, to see how pitch can change. So in our second example, we can see there are more compression areas and rarefaction areas than the one before. This means whatever is making the sound is vibrating more quickly. So faster vibrations, which means this sound has a higher frequency, and the sound that we hear then will have a higher pitch. higher pitch. So the thing that might make this sound could be a bird. A bird's whistle has a much higher pitch than a person yelling. Okay, a third example now. In this case, we have fewer compressions and fewer rarefactions being made every second. So whatever is vibrating in this case, as the sound moves along, must be vibrating slower than the other two examples. So this one has slow vibration, and that means the frequency of the sound wave is also slow. The frequency is low. And then the sound that we hear, if it looks like this, is going to have a low pitch. It will sound lower to us when we hear it. Something that might make this could be a bass drum. When a bass drum gets hit, the vibration is slow and we hear it as a low pitch sound. The last thing to look at is how quickly does sound actually move through materials. And you might have heard about the speed of sound, but what people mean when they mention the speed of sound is actually the speed of sound in air. Because, as we've learnt, sound can move through all different types of materials, but most commonly we hear sound through the air. And in the air, sound moves approximately 1,200 kilometers per hour, which is about 330 meters every second. Meters per second. But this is only in air, which is a gas. Remember that the particles in a gas are spread apart with big distances between them. In a liquid, particles are a bit closer together, and in solids, particles are so close that they're all basically touching each other in an ordered pattern. Gases, liquids, and solids. So when sound moves through any of these different materials, it will move at a different speed because of one main factor. And it's because sound waves need to move by the particles crashing into each other. So sound waves move by particles bumping into each other. We can imagine that as an area of compression happens, the particles in that area will then push against other particles near them, and that causes the sound wave to move along. In a gas, there are big gaps between each particle. So it takes a while until one particle bumps into another one. But in liquids, there are smaller gaps between the particles, so it doesn't take as long for a sound wave to move through a liquid. In other words, the sound wave will move more quickly. And in a solid, the particles are so close that sound waves move really quickly through solids. And as an example, sound in water moves in water, which is a liquid, sound in water moves at about 5,000 kilometers an hour. Much faster than in air, which is a gas. And in steel, which is a solid, sound moves at about 18,000 kilometers per hour. Because the particles are much closer together and they bump into each other more easily, so the sound wave passes through more quickly.